Okay, I'm not too sure why it can't share what I want to share. Maybe if someone could provide guidance with that.
Let me try to figure out. Maybe Steve, when you share, you can share your application, then go to the window that you want to, or the tab
Oh, okay.
you want to share.
Okay. It should be fine now, right?
Yeah, it's coming up. Yeah, it's okay now.
Okay, sure. So the first page, that's just what I told us earlier about the whole, it was just, that's one of the plants we've done somewhere in Kijabe area. It's a 150 kilowatt, just a picture for my first page. I'll move to the core of, I felt we needed to start with understanding the basics of solar, but I'm not going to start with introducing what solar is. I think so far all of us should have understood that solar PV really it's about solar that we use to generate electricity, if I could explain it in a layman's language. So some of the components of the PV system, if you want to design systems, you need to understand what makes up a PV system. That's what I thought we need to start with. And the key areas that would make up any PV system, regardless of whether it's off-grid, grid-tied, or hybrid, the common things that must be there, of course, are the solar modules. Under the solar modules section, I listed some types of solar modules that we have in the market. This is based on their make, based on which type of materials are used to make them. We have the monocrystalline. I'm sure most of you have heard of this. They are the most efficient, rather, solar panels. They used to be the most efficient before an upgrade. And so these are pretty much made from single crystalline materials. Poly is just polycrystalline. It's same material as monocrystalline, but from several silicon wafers. And then we have PAC. So PAC, this is where I'm going to base most of my discussion at. That is passivated emitter and real cell. This is just an improvement that has been done on the old monocrystalline modules or solar cells, to in a way that it manages to, when there's a problem that initially the monocrystalline had, in that they could reflect back light when solar rays fell on the modules. So the pack helps with that. It reflects light back into the cell, and also it reduces the electron recombination to, prevent the inbuilt of to prevent the electrons from crowding up, and then they interfere with the flow of electricity within the solar cells. So thin film, the next one is thin film solar, the thin film solar modules. The main difference between this and the mono poly is that they're made from different materials. So as you can see, we have the three types. You will see the names. There's amorphous, there's the cadmium, the copper, indium, gallium selenide. So the only difference they have is that the type of materials used to make, the chemical composition. All the ones that have been listed there, monocrystalline are, so far they have efficiency of more than 20%. But when the monocrystalline has been improved using the pack, we are looking at efficiency levels almost around 23 to 25% so far, the ones that I've seen in the market. We are yet to go past that. So that's pretty much for solar modules if you needed to understand. So if you are designing a system based also on other factors that you need to consider, because as much as monocrystalline offers you best efficiency, things the thin film will work best, where we have high temperatures and all. So it's all about a trade-off of what you really want to do. But us in the field, since we are in the business of guaranteeing power, the monocrystalline provides better returns on that than the rest. So on to the next, we have batteries. For batteries, most people who are not in solar, when you tell them of batteries, they would probably just think about the car batteries and all. But there's a difference. If you look at my description, I was very specific on, for example, the lead batteries. I wrote there deep cycle, because the deep cycle batteries meant for solar are different from the high, the starter batteries that are used in vehicles. The chemical composition and the metals used within are different for different capabilities. In vehicles, we need the batteries to be able to discharge a high level of current within a short time for you to start your vehicle. But for in solar, we need the battery to be stable, so that, again, longevity of the batteries. So we have two main battery types so far in solar that most people use. We have the lead batteries. Lead batteries also are further categorized into two. We have the flooded and the valve regulated lead acid batteries. I'm not going to give us more in terms of the chemical composition of it, but this is something for you to know, is that lead batteries definitely are less efficient in comparison to lithium ion, which is the only problem with lithium is that it's very expensive. But in terms of lifespan, we have lithium batteries that do 10, 15 years. But for the lead acid batteries, most of them, 3, 5 years, then you need to change them. So there's that. We'll look into that later on when you get to the design bit. Oh, I hope I'm not too fast.
Yes, you are okay.
Oh, I'm fast. No, when I'm fast, someone can just let me know so that I don't skip or leave people behind.
Okay.
Okay. I'll proceed to the next one. The next component which is also important in any PV system are the inverters. So for inverters, we have different types of inverters depending on which type of solar PV system you have. Up there, the first I have a grid-tied inverter, or different names. Some people will call them string inverters, but pretty much these are inverters that you feed DC to them and they give you an AC output, but they can't charge batteries. Their specific use is only to give you power during the day. They can't work at night or anything. The only thing they need is a reference voltage from the grid, that is, in our case, KPLC, or in ones that are some can work. They can work with generators as well, as long as that reference voltage is provided. The voltage of the grid and the generator must be within the specified inverter AC voltage range for that to happen. Such systems, such inverters are used for the C&I scale solar PV plants, because those, in most cases, the clients don't need battery systems for the reason that battery systems are expensive and also very difficult to maintain. So most of them are just after savings. They just get these inverters. They work during the day from when the sun rises to when it goes. The next ones that inverters that most of us are accustomed to are the battery inverters. The battery inverters, pretty much their work is to discharge the battery. Some of them have been built with the capability to charge and discharge. The ones that can charge and discharge batteries, they're called inverter chargers. If any of us has ever had the opportunity to work with an inverter, for example, Victrons, yeah, they have this range of inverters. There are also other batteries inverters that only discharge, they can't charge. The last one, there we have hybrid inverters. So hybrid inverters pretty much does what it takes the first one and the second bit and houses them together in a single unit. They can get connected to grid. They can produce AC directly from the modules. At the same time, they can charge and discharge batteries from either the AC side, some of them, and from the DC side, that is the panels. So yeah, we'll get to learn more about that later on. The fourth one are charge controllers. So charge controllers are used mostly in DC coupled systems. I'll get to explain what a DC coupled system, but pretty much it's where you connect your solar panels to charge the batteries first before they go to your loads. So that is from solar panels to a charge controller and then to the battery is when now you have your inverter to give you the AC output. Charge controllers mainly regulate the currents and voltages, as I've written there, to appropriate levels needed to sustain battery charging. So this, I would say, they're like a safe net for your batteries. They would know when to charge, when to discharge. They will vary the voltages and currents depending on the DC input at a given time during the day. Charge controllers can be classified into two technologies, really. These are the pulse width modulation charge controllers and the MPPT, which is the maximum power point charge controllers. So for pulse width, let me mention that they are not, of the two, they are not very efficient. It's an older, I would say it's an older technology compared to the MPPT. But in pulse width, the way it works is you have to make sure, for it to be very efficient and to help you, you have to make sure that the module you use, voltage of that module must be equal or close to the system voltage or the battery voltage that you're charging. For example, if we have a 12-volt battery, when we're using a pulse width modulation charge controllers with that technology, we have to look for a 12 or anything that is, it can't be lower than 12, but it can also not be 30 volts. We need to try as much as possible to find a panel that is rated as about 12 volts, yes, for that to really help us. If we were, for example, to go for modules that are 40 volts, this system, you'll end up that you'll not get the required, or rather, I would say you'll not get the required output from your module, because pulse width modulation will force the voltage. First, if you connect the panel to the charge controller, it forces the voltage to come lower, so that if, for example, the battery has been discharged, the voltage of the battery, most of the time, it reduces slightly. So when it charges, the module voltage must be brought lower so that as the battery charges and it increases in charge, the charge controller as well will let in more voltage from the panel. So, but it does not, when it takes down the voltage, it does not do so to the current. It's for the module to give you the power that it has been rated. For any decrease in voltage, for you to get the exact power, you have to play around with the current, which means you have to then find a way of increasing the current output. So the pulse width modulation technology does not really offer you that the ability to do that. On the second one is the MPPT. So the MPPT, if we are familiar with what we call the IV curves in solar, that is the way tracing the currents and the voltage within a solar cell. So the MPPT is, again, during charging, it will, if for example it's a 48-volt battery system, or rather, let me use a lower one, if it's a 24-volt battery system, and we are using the bigger modules that, for example, are rated at about 40 volts. So the MPPT will also reduce the voltage to what really the battery needs. But in exchange of that, the power at the input side will be equal to the power at the output side, in the sense that it will now increase the current. While it is reducing the voltage, it increases the current for it to make sure that if I was getting, for example, I have a 500-watt input, DC input, on the output side, I will still get my 500 watts, regardless of whether the voltage, my module voltage, has been reduced from 40 to 24. So for better efficiency and best system, you need to always consider MPPT. But of course, there are instances when PWM, you will consider. Most of that is based on finances. When you have to do that, it's probably going to be because of the price difference. MPPT charge controllers are a little bit more expensive. And also, if you happen to come by the small modules that are rated at 12, 24, or whichever voltage level your battery system is. I'll move to the last bit, which is I gave it a name like other balance of systems. Other than solar modules, let me say that other than solar modules, most of the rest of the components, most of the time, in the solar field, you will hear them talking about BOS, or balance of systems. Most of them are categorized under that. But in this case, I left. So anything else that you would need for for the efficiency and for the best work of your solar PV system, that is what will fall under there. These are your cables, your switchgear and protection, everything else that you'll need, the consumables, whatever it is, it can fall under there. When we're moving to the next subtopic of that is now the types of PV systems. Initially, if you can recall, when I was talking about the different types of inverters, I gave like 3 types. Mostly, this also pretty much gave us a clear indication of what our types of PV systems could be. Yeah, so we have pretty much, I would say, 3 types of PV systems. We have the grid-tied PV systems. In grid-tied, here, modules, as I explained earlier when I was explaining the grid-tied inverter, the modules are connected to the DC input of a string inverter or grid inverter. That inverter then gives you AC output. The AC output is used as generated. It cannot be stored. It's not being stored, rather. It can be stored in a different setup, but it's not being stored in this case. So the main thing with this is that your inverter AC side, the cable from your AC output side of the inverter, is always connected in parallel with the incoming grid. the incoming grid cable, or whether it's a bus bar, depending on the layout, the electrical layout of a facility. But you have to connect them in parallel. Most of the time, if, for example, it's easier for you to have the grid tied when it's only connected to the grid than when you have to incorporate a genset or a generator. Reason being, it's easy to control, and in this case, solar is always given higher priority. Let me use an example. If you're a facility that consumes, or rather your load is 100 kilowatts, and we have a 100 kilowatt inverter, during peak sun hours, when your solar can give you 100 kilowatts worth of power, you will only be using power from solar. The grid will just be there as standby to provide the reference voltage needed by the inverter for it to generate power. If, for example, if a cloud, passes over where your area within a few times, and now your inverter can only generate 50 kilowatts, the priority will be given to the inverter to give you the 50 kilowatts. Then the grid will bring in whatever the balance that is required. Yeah, it's always going to be that type of trade-off. When one rises, the other goes down, depending on the environmental conditions that really affect solar generation.
Excuse, Steve.
Yeah, sure.
Yeah, so someone says cannot see the strength here, so maybe you can put them on strength show
Sorry?
so that they can be. You can
Oh,
put the strength on strength show so that they can
yeah.
be a bit bigger. Someone said you
Oh,
cannot see from the head.
and then better? Sorry. Yeah, sure. Thank you. So let me explain the generator concept. When you have to tie your grid-tied inverters to work with the generator, this is in cases where you don't have a KPLC, for example, in our case, or rather the grid is down. Then there is an extra design due diligence that you must have, in that you must now program your system to work, for rather your generator to work at the least power, to give you the least power. Most of the time it's around 30%, depending on each, and this is something that varies with generator suppliers, but most generators, it's around 30 to 45%. That is the least they can operate, the least load they can operate at and still remain efficient. Anything lower than that, then now they will no longer be efficient. So you want your solar to be operating with the generator, but the generator has to supply 30% of the load. So the 70%, that is what your solar can supply. The other thing is that you need, it only makes sense to run such a setup when you're going to save on fuel. So you need other equipment like by the name of fuel savers. So this will regulate the amount of fuel that the generator uses depending on the load output, depending on the load that is connected to it, and depending on the solar output at each and every given time. So by that reason, definitely running generator is expensive, because during when you are buying the system, it's expensive. You need extra equipment, but also running it's still cheaper to run with the grid. The next one is off-grid solar PV. This is what most of us are accustomed to, but pretty much this is where we're going to have batteries. We're going to have the battery inverters, and generally, the whole system is not connected to a grid. Yeah, it's not connected to. In Kenya, it would not. You don't have Kenya Power, but they could still use generators to sometimes charge their batteries. So that's that. The next one is hybrid systems. Hybrid systems, again, it's just A combination is like having the grid with energy system. Like you have a the grid tied, and then you incorporate like batteries into it. Yeah. So that's what hybrid means. Okay. So there we have a picture of what I was explaining uh, regarding the grid tied systems. You can see there we have a PV inverter, and we have solar panels, then we have the public grid, then loads. So if you're so keen, you will see that the output, the AC output of the inverter, the picture shows two arrows. It can either go to the loads and also go to the public grid. Now that we call it grid feeding back in Kenya, we call it grid feeding when now your power is going back to the grid. It's still not yet allowed in Kenya, it's illegal. So between the interconnection point and where has been rated public grid in Kenya, you have to incorporate uh, cities and an energy meter. This is supposed to monitor what you're getting the load, what you're getting from the grid. And this is used by the inverters, the inverters are smart to regulate the output. So for example, back to my example over the 100 kilowatts, if for some reason your loads go to zero, yeah, the grid is available. It's midday on a very good sunny day. The climate, the general weather is good for PV production. The inverter will reduce its generation from the 100 kilowatts that it would have been able to give you to zero. It will stall, really. So we are not allowed to feed back to the grid. So that's something that, again, you have to consider during your designs. This, if you're not planning to use generators, that monitoring point must be, and the interconnection point must be before a changeover. Yeah. So it's a case by case basis, but that's the general scope of it. Let me move forward. We have off grid PV systems that we were talking about. So in this setup, this is a DC coupled system, a DC coupled in the sense that we have the PV connected to a charge controller, then the charge controller is connected to the batteries. In DC coupled, the batteries are being charged by DC power directly from the modules. Later on, there is an AC coupled system. In AC coupled system, the battery is being charged by AC power that is converted to DC using a battery inverter. Okay, so it's pretty much depending on what charges the battery. In a AC coupled, we have an PV inverter like the one we've just seen in the other slide that converts the DC from the modules to AC. Then that is then converted back to DC using a battery inverter to charge the batteries. So that's the difference, really. This is an off-grid setup. You'll notice that we don't have grid anywhere, but there is provision. You can always have provisions for generators depending on which battery inverter you're using. Some can support that, some cannot. So it all depends on what you've selected to use. The hybrid systems, again, what I was telling us earlier, you will notice that we have DC from solar panels. Now, this is a hybrid PV system with a single unit of a hybrid inverter. It could be hybrid, but you have all these functionalities of the inverter separately. Yeah, but in this case, we have one inverter, a hybrid inverter that has the ability to take in solar PV modules. It has the ability to charge and discharge the battery. At the same time, it can connect to the grid. Yeah, so that's what hybrid solar really is about. The setup, as I've said, can change depending on whether you're using individual inverters. I can decide to go buy two different inverters. I can have one that is a grid-tied inverter, and then I can have a battery inverter, then I'll still have the same functionality as to what is offered to us by this single inverter. So this is what I was just explaining earlier on about types of solar PV energy storage systems. Yeah, it's talking about the energy storage systems because it's a factor that's related to batteries. In the first case, we have AC coupled. If you are keen, let's begin at the let's follow it up from the PV array. That is then we have the DC output. It goes to what they have called an interactive inverter. This is just another name for a grid-tied inverter. And then we feed the AC loads as well as feed a DC inverter, what they have as a multi-mode inverter. It's a multi-mode because it's that's like a bidirectional. It's a bidirectional inverter. It can charge and discharge. If you look at the arrows as well, you'll notice that. So from the AC side, we charge our batteries using the AC output of the grid inverter. Yeah. So in that case, we say our energy storage system is AC coupled. Yeah, because the panels first go to the DC first is converted to AC, then after that the AC is then brought back to DC to charge your batteries. In terms of efficiency of the charge, it is not the most efficient way of charging your batteries for the reason that you have to do a lot of conversion from AC, DC back from AC back to DC and all that. So there are instances where you might not be advised to use this because also there are some battery systems that if, for example, they were to go off due to they were fully discharged to 0, for example, or 1, whatever it is that they've been set to. They cannot be, and then most of these battery inverters need the battery, they need a voltage from the battery for them to be on. So in the event that a battery is fully discharged and it cannot come back on, it means this multi-mode inverter cannot come on. When that happens, then you cannot charge your batteries. So in such cases where you think that such a thing might occur, you want to avoid this setup. Or even if you're having this setup, you still have to incorporate a little bit of DC coupling on the batteries, in that you'll divide your PV array. Some of it will be coupled to the batteries using a charge controller to enable it to charge, to enable it to charge in such cases when it's fully discharged, so that the multi-mode inverter can always be on. On the next, just next to it is the DC coupled system. In the DC coupled system, again, if you follow up from the PV array, you will go to, you see it first goes to the charge controller. And then from the charge controller, the batteries, and then from the batteries is when now it goes to the multi-mode inverter. Yeah. So in this case, the generated power, most of it usually passes through the batteries up to such a time when the batteries are fully charged. When the batteries are fully charged, then whatever is coming in from the modules will just go through the batteries, but not really be stored there. It will pass through and go to the multi-mode inverter, pass through the charge controller, go through the multi-mode inverter, and it's converted to AC straight away. So, again, this is also, but the cases when you can consider using DC coupled, these are small systems, mostly for small scale systems. Yes, it's good to have, the normal residential houses and all. This will work perfectly. But for industrial scale, those are the cases where now you'll need to consider using AC coupling, for the reason that it's easy to, most of the AC inverters are multi-MPPT inverters. They can take in a lot of power from the PV arrays. In the other case, most of the charge controllers are limited. I know of good brands, which so far, most of them can only do around 250 volts of, that's the maximum, the largest charge controller they have. If you compare that to PV inverters, that can go up to about 1500 volts. So that's, they can take in a lot of panels. Yeah. So for industrial scale, that maybe you need energy storage systems, AC coupling will be a benefit. The next, I hope guys are noting questions, but if you feel that maybe you can't wait with the question and you might forget it, it's fine. You can just ask, okay? So that we avoid also having it being a unidirectional conversation. So onto the main bit of what we are planning to do today is now talking about design of solar PV systems. We've already looked at the different components. We've already looked at the different types of couplings and different types of PV systems. So this design basically covers all of them, in that it covers all the type of PV systems. It just depends on up to what stage does your PV system cover. For example, if we are talking about grid-tied systems, we are the same way we are going to do a load estimation, with the same way we are going to do solar PV array sizing, and then the inverter sizing. That's the same for all of them. When you go to off-grid and we want to introduce batteries, the formulas are there, charge controllers. So if you can get to know this design procedure, you in most cases you will be able to design all the PV systems. Yeah, this is the basic knowledge of solar PV design. So on the first step is load estimation. It's not, this is the first thing that you must do as a designer. You must know your load and energy requirements. If it is a home, you have to know what loads do they have in that house. How do they use them? What are the number of hours they're used? All that. You need to know how much energy that household or company, whichever premise it is, you need to know how much energy they consume in a day. So there, I gave out 3 points there. You need to know the total power in watts. Yeah, for all the different loads, lights, whatever it is. You need to know that. You need to know the total energy requirement per day. And you need to know the last part is the load diversity factor. So you'll come to realize, if I can narrow it down to our houses, we have a lot of electrical equipment. Yeah, but it's not every time that all of them are running. For example, you'll only probably use your lights 90% of the time at night, but not during the day. Yeah, and even if you're watching TV, for people who watch TV, it's not, you don't watch TV 24 hours. So what I'm trying to drive to is that you need to know diversity factor. Just, it's a ratio of your total loads and that probability that, how many of them will be on at the same time. We're trying to get to that point. How much of the daytime is it on? This will help us tackle point number one, that is total power in watts, because it will help us know the total loads that can be connected by this client or by you at the same time. This will prevent us from oversizing an inverter. Yeah, so again, costs. If it is an industrial scale, that is a lot of, it will prevent us from generally oversizing our system, which again also leads to wastage. So ways of doing load estimation, the best way is if it is a, a premise that is already work connected to grid or any other power supply generators, you need to do what we call power logging. So you need to go there with power loggers, you connect them for depending whichever time frame you need, which will work best for you, a week, 2 weeks. Try to have this done during a period when they are operating at their maximum, at their peak. So based on that, you'll analyze the consumption and you will size the system. The other way is using the bills. So for bills, depending on whatever you're sizing, if, for example, your client wants to move away from grid, Kenya Power, then you have to really be good at analyzing the bills. It's not the best, but you have to really analyze the bills. 24-hour or rather 30, you would start from the 30-day bill. You have to subdivide it to a point where you can understand what this client needs or what the power requirements are per single day. And in off-grid, you must size your system to be able to give you the whole of that energy within a day. If it is a grid tied, for if you've ever had the opportunity to look at Kenya Power bills, you'll come to realize we have the high rates and the low rates. So high rates, mostly this will cover the most of the time it's around 16 hours of the day, which most of these 16 hours are daytime data. So for grid tied, you want to narrow your focus onto the high rate consumption. Yeah, and then you'll then subdivide this by 16 hours to even get the power from that. Yeah, but generally the best way to do it is do a logging. If it's the first time the client is, if they've never, it's a new plant, then you want to do the load estimation, in the sense that a projected load estimation based on what this client is, or rather what you're planning to have, yeah, as part of your electrical system. All of that data needs to be captured, needs to be tabulated. You need to calculate the energy and the power. I had to take a lot of time there because without that, really all the other steps will not make sense. Yeah, if you've not done the first step correctly. The next step is you need to size your array. So an array is these are just a bunch of solar modules connected in either series or parallel. Yeah, if they're connected in X number of solar panels connected in series, that is what we call a string. Yeah, but more of multiple strings, a group of strings, that is what we call an array. But there are instances when an array can just be a single string, because you can have a single string. Yeah, so that's the difference. So how to get your solar PV requirement for a given site or system? Again, from the formula there, let me just read it out. The total number of modules required is equals to the total watt hours. This is the energy. This energy was gotten from the first thing that we had to do, the load estimation. Now, this, for example, if we find that you need, let me use you need 1 unit per day. You use 1 unit per day. That's 1,000 watt hours. This 1,000 watt hours is what you have to multiply it by what we call a loss factor. So let me delve into that a little bit. When designing solar systems, there are losses, and these losses need to be factored in, and also the general The way to factor them in is most of the time you have to multiply whatever your energy requirement by a factor of about 1.2 to 1.3. So if we had the 1,000, the 1.2 to 1.3 will cater for most of the losses. These are losses due to the inverter efficiency, losses due to cables, all that, all the electrical losses and environmental losses that could be brought about by different scenarios in the environment. So most people will use around 1.2, some will use around 1.3, depending on, just remember that it affects your system size in the long run. So you want to try as much to be efficient with that as well, and balance it to how much you're willing to spend on the system. But the total watt times the loss factor, for example, 1,000 watt hours times 1.2. And then we need to then now divide that. That is like now 1,200. We need to divide that by the rated power. So up to this stage, you should have already decided and done research on what modules, solar modules are out there in the market, which one is best suitable for my, for my use. So for example, we can, if we have to go with the high rated modules, I would go with around 550. So that's 550 watt peak module. So there, under the rated power, that is like the 550 watt times the location's peaks and hours. So this is what called insulation. On this last point, the location peaks and hours, as much as we have 12 hours of the day, but the sun is not always strong throughout the day. So peaks and hours are those instances where the sun, the insulation, or rather the radiance from the sun is thought to be at least 1,000 watts per meter squared. The general energy we can get from the sun rays. So it changes, it varies from different places. For example, in Nairobi, it's different to what you'll have in Eldoret. It's different for what someone is going to have in Kisumu or any other place within the country. So this as well, there are websites, there are public websites that you can get this data from, the peaks and hours. Yeah, the public websites, you Google, you get this from. For example, in Nairobi, it's about 4 to 4.3 hours in a day. For some places like Kisumu, it's a little bit higher. Some places it's 3. So it depends on the general climatic conditions of a given area. So, for example, I'm going to use let's say 4 hours. So it's like 1,200 divided by 150, like 550 times 4 hours. That will give you the total number of modules you require. You might get a decimal number, a number with decimal points. It's always best for you to try and round off to the next whole number. Yeah, if you still want to achieve your energy requirements. So the general assumption here, it's not assumption, the fact is we want to achieve 1,200 watt hours with our example, but we need to do this in this peak sun hours. So as much as the 1.2, or rather 1 unit is used in the day, but we must get it during the strong sun hours. So we have to get it within those 4 hours. Yeah. That's the reason to why we need to divide by that ratio, by that number, the peak sun hours. Once you get that, then now you move to the next step, where you're going to now get your batteries. So for batteries, there are different ways you can size your battery. You could decide that I only need 1 hour storage, yeah, of my whole energy requirement in a day. I only need storage that can help me out yeah, for 1 hour or 2 hours. Or you might, if you are totally off grid, you might think about, no, I just need to store total a daily energy requirement. I need a bank of that size. If you come to the formula, batteries mostly the battery banks are sized in what we call amp hours. Yeah. So there's the amount of current that bank can give you for a given battery voltage. Yeah, or bank voltage. So the way for you to calculate the total amp hours that you require, for example, is the total energy you need. That is what we got from now load estimation times the days of autonomy. Days of autonomy. This is a term that is used to refer to the days that you need your battery system to continue supplying you with energy, assuming that it never gets recharged for any for any reason. Definitely, there we can't say. Well, the assumption is that there is no sun at all, but it's very hard for that to happen. So mostly due to cloudy conditions or just a rainy day the whole day. So the days of autonomy is something for you to decide. The decision needs to be really looked into because these days, any day that you add, it means more batteries are needed, which means more costs. So most people do between 1 to 3 days of autonomy, depending on. So for 1 day of autonomy, it's just that your battery will only sustain your load requirement, your energy requirement for 1 day, if at all there was no, it was not, recharged. For 2 days, again, it's just multiplying this total energy by two. So 3 days, that is the whole thing about it. Then now you need to divide this by the efficiency of the batteries. This is something that you will get from the data sheets, different battery data sheets, depending on which battery you're planning to use. If it is a lead acid, you would have by now decided on which equipment you want to settle on. Mostly around 0.8, 0.85 efficiency, zero point 0.9. It varies depending on which equipment. Then the next point there is efficiency multiplied by DOD. DOD in full is depth of discharge. There's also something very critical in battery sizing battery systems. A depth of discharge is how much you can drain your battery. Yeah, after which you have to recharge it. So if one day you have if you go look into any battery data sheet, you look at, they have something called life cycles. A life cycle of a battery is the amount of time or the number of times this battery will be charged and discharged. If you see, like, for example, most of them lead acid 12 volt 200 ah batteries, you'll see something like 700 life cycles. 700 life cycle just means you've charged and discharged this battery 700 times. Yeah. So if that was you charging and discharging this battery daily, that's just roughly over about over 2 years. And then after that, this battery will be, it will need you to change it. So the depth of discharge, for example, if you can use a number like 30%, so there's more like, if my battery is 200 ah, I can only discharge 70% of it, after which I have to charge it again. Now, these are settings that you will do in an inverter to help you with that. If lead acid batteries, mostly people do a DOD of 50%. So even if, for example, if ideally I need one battery of 200 H12, that's 2.4 units. If I give a DOD of 50%, it means I need two batteries of 2.4 Ah. So I have a total of 4.8 Ah. So if my energy requirement, for example, is 2 is 2.4 units in a day, I can only discharge my 4.8 bank to 2.2, 2.4, sorry. Yeah. After which, so in this case, I elongate my battery lifespan back to that the mathematics we did earlier, 700 life cycles. If I have my battery, the DOD, the depth of discharge, then I can get an extra 1 or 2 years to my battery. Okay. For lithium batteries, it's a little bit different. Most of them have depth of discharge, some 100%, and they could still go for 10 to 15 years. So for lithium, yeah, it's something that really, it's not a big deal per se. But for lead acid, it's something you really need to pay attention on. Otherwise, you will be blaming the battery manufacturers that they gave you a defective battery, while in the real sense, you didn't factor in the depth of discharge. So after calculating the total OH, we need to get the number of batteries. I left something there after DOD. I left the system nominal voltage. The system nominal voltage, this depends on how you are going to string your batteries, either in series or in parallel. Yeah, if it is a 24 volt, 12 volt battery bank, 24 volt battery bank, or 48 volt battery bank. Most the voltage that you require or you use will depend on the system size. Yeah, if your system is like a 1 kilowatt plant, you can do 12 volt. But the moment you start going above 3 kilowatts, 5 kilowatts solar plant, then probably it's best for you to consider doing higher voltage, 48 volts, for example. The reason being, you reduce your ohmic losses, reduce the cable sizes that you need. So yeah, it's a trade-off in design, and also just the safety. It's a little bit safe because low voltage means high current for equal amount of bank. For example, if I have 30 amp hours bank, or rather, if I have a 2.4 kilowatt hours bank, if those are like that is one battery, then it's 12 volt. That's fine. But the moment as I increase it, if I have to increase the energy that I gain, I need to do a trade-off of it's safer for me to have a 48 volt with 4 batteries, yeah, of 12 volt than having a 12 volt with 4 batteries. In that the current would be excessively high. In case of any shorts, it's way dangerous than the 48 volt one. And also just in terms of cable sizes, it's cheaper to have it in 48 than in 12 volt. So it will depend. But as a general rule of thumb, system size up to around 1 kilowatt, you can do 12 volts. Up to around 2 kilowatts, 3 kilowatts, you can do 24. But anything above that, try to stick to 48 volt systems. So the next one is inverters. An inverter is total maximum power over the inverter efficiency. So that is what we talked about earlier. I'm going to be moving a little bit faster. See, so total maximum power over inverter efficiency. Most inverters, this inverter efficiency, something that you can get from the inverter datasheet. Yeah. So for example, if our load is we know that our total load is 2 kilowatts. So we take like 2 kilowatts divided by inverter efficiency of sometimes it's 0.9, sometimes 0.95, yeah, depending on which inverter you're using, to get the inverter size that you need. If the math that comes after that calculation is that particular size of inverter does not exist in the market, always go for the higher. For charge, for the charge controllers, again, it's now back to your number of modules times the short circuit current of the modules, because that's the maximum current you can get from that module is the ISC, times again another this again safety factor of 1.2 to around 1.3. This will give you the size of your charge controller. After getting that, again, you now have to figure out what charge controllers are there in the market, and how many do you need to achieve this, that you the size that you, because sometimes it's going to be higher than what actually exists. So you need to do multiple of them and combine their outputs. Other balance of systems, these are cable sizes. Cable sizing in solar PV is the same as you would in when you're dealing with an AC system. Again, voltage drop, something for to consider. Uh, Currents, the inverter currents, again, battery currents, but something to consider. The distance, again, something to consider. MMS, that is module mounting structure, it's different depending on which roof, ground mount, whatever you want to mount it, that will dictate which mounting structure you use. And also just weight, things like that, the weight, wind load, and all that. Yes, that's something to factor in. For switch gear and protective devices, again, like cables, applicable the same way you would size them in a common AC system. That's the same way you need to size them in a solar PV system. For example, if someone tells you your inverter maximum output current of your inverter is like 80 amps, then in that case, for if you needed a breaker, your breaker, you'd multiply it by a factor, the current, the 80 amps, by a factor of, again, another 1.2. So your breaker should be around 100 amps. Yeah, something like that. That's pretty much how you do it. Let me move to factors to consider during design. I talked initially, I told you guys about stringing. I talked about stringing, which pretty much is the number of solar modules you have in series. This ends increasing the voltage for a constant current. Yeah, parallel the other way around. So in a string, first of all modules in a string needs to have everything similar, be it the number of strings, the orientation, the side they're facing, how much, everything about them needs to be the same. They must be of the same current voltage, in the sense that they need to be the same product. If it is 550 watt peak module, all of them must be 5. If it is 100, all of them must be 100 watt peak. So a string is a group of modules connected in series, as I've stated there. Again, the string size depends on the module parameters. That is mostly the VOC and the ISC of the modules. Inverter or charge controller parameters. Again, these are also the maximum voltages and current operating, maximum and minimum operating voltages of inverters and charge controllers. Yeah. The next one is orientation of modules. So orientation, these are tilt angle. A tilt angle is pretty much how much the module will be slanting. It could be 5, 10, 20. Just know that in Kenya, we are pretty much within the spheres of the equator. So we don't, for us, the flatter the module, the better it is. Yeah, the better output you'll get. But also you don't want to have it at completely flat on the surface, because you need your module to self-clean. Self-cleaning is when it's rained on and that water can wash away the dirt from the module without building up. If you had it flat, it will build up. The azimuth is pretty much the orientation of your module away from the true north, from the true north. So again, that's something that software is used to calculate how much it's going to, because, for example, an east-west, if your module is facing east, it will be very good in the morning, and then later on, depending also on the tilt angle, in the evening, the west-facing module is going to perform better than the east-facing module because of the sun, the sun direction. A north-facing and a south-facing also will depend on which month, which period we are in the year. For example, in June and December, when the sun changes position. So those are things to consider. The meteorological data, these are, again, we talked about peaks and hours earlier. I'm not going to repeat that. We have temperature. Temperature, again, remember all your modules, the modules are rated at STC. There's a standard test conditions. Standard test condition, the temperature is 25 degrees. So if someone tells you this module is 300 watts at STC, it just means at a thousand radians and at 25 degrees, this module will give you 300 watts. But the moment the higher you deviate from 25, you go to 30, 40, of which most modules will operate between 40 to 60 degrees most of the time. Yeah, in Kenya, you come to back to the basics of electricity, and in terms of the VI and uh, R relation. If you increase temperature, you increase the resistance within the cells, the solar cells as well. So that again depreciates the output and the efficiency of your module. Wind, a key factor in that, yes, it depends on, it helps you determine which mounting structure you need, but at the same time, more wind means uh, like cooling. With the wind also comes the aspect of cooling. So if your modules are going to cool at a higher rate than if they were somewhere else with low wind, then they will perform better than the one that is at the different location. So that's something again that you have to factor in. Most of orientation modules and meteorological data, you can these are things that now help you when you're designing using softwares. For example, PVSys. Yeah, it will import this data, and then for like a given 7 years or so, then it will use that data to give you to calculate your expected solar performance within a year or something like that. So system losses, again, we tackled it earlier, but system losses, we have thermal losses. I've just discussed that. This is based on temperature and wind. It's a factor. In PVSys, for example, you will see a thermal loss, something like a thermal loss of 29, 20, and 15. The higher the thermal loss factor, the better the better that module will lose heat. Yeah, so the better performing it will be. So for example, modules that are ground mounted, thermal loss factor is about 29. That is if you're doing the PVSys, by reason being that both sides of the module is open to wind flow. So back to again, wind flow, that free airflow means the module is able to cool faster. For if you are doing your module installation on a mabati roof, then you've reduced that distance, the clearance underneath, so the wind flow is not going to be that great. That is when we consider using a factor like 20. For 15 on PVCs that you use when your module, the backside of your module, is in direct contact with the surface, in that there is no room for wind to flow or anything to flow underneath it. So it's going to have worse thermal losses. That's something that you need to factor in during a design. Again, temperature uh, affecting resistance affecting your output. Ohmic losses, these are losses due to the copper losses in cables, both DC and AC. I should mention that we don't use the AC cables, yeah, the typical ones we see being used in housing units and all. They're not recommended to be used for the DC side of your solar PV. The reason being that, again, they are not they're not UV protected. Solar stays on your roof or whatever it is for about 20, at least averagely 25 years. So you need your cable to also be able to withstand UV from the sun for that amount of time. DC cables are specifically protected against that. But again, ohmic losses, back to voltage drop. It depends on which company and also country, but it's always good to have. Some will tell you 1.5. Some people will tell you they need 2% maximum voltage drop. Some people will tell you they can go up to 3%. So again, that as a designer, you need to understand which client or who are you designing for, what are their requirements, but also generally you have to be aware of the laws, the Kenyan laws about voltage drop. Light-induced losses on modules. Uh, for the moment the module has been put out there in the sun, it starts to depreciate, yeah, because of light. So that's pretty much what light-induced losses are. The modules will always depreciate once they've been exposed to those environmental conditions like light and all. So over the course of 25 years, or the span of the lifespan of the PV plant, that will happen. Soiling losses, this is just loss due to soil settling on top of the glass, the solar module glass. This needs to be cleaned regularly, especially when it's not raining, and especially when you're in an area that has a lot of loose soil which settles on top of your modules. Losses due to shading, again, when you're picking an area to have your solar panels, if it is possible, avoid all shading, anything shading, avoid them completely. Because any module, back to stringing, if you have a string of 20 modules and one of them is shaded, your solar plant will work at the efficiency of the worst performing module. So if out of 20 only one is shaded, then the whole plant is going to work at the efficiency of the shaded module. So if it is not able to generate anything, it's a really thick shade blocked completely from the sun, and it can barely generate. It's safer to say that your plant is down. You want to avoid shading at all costs. Other factors to consider, we have equipment positions. That's for inverters, again, solar panels, uh, everything else, because again, maintenance, you need that all your equipment should be in a position where you can maintain them. Inverters have this clearance space needed around them for cooling that you need to factor in. Yeah, and batteries as well have clearance space around them for cooling. Batteries, you don't need to put your batteries very far away from your inverters. You should try as much as possible to have them less than 2 meters away. Yeah, because batteries, the losses are a little bit higher. So you need to try that. You need to try, and also you want to try and minimize the number. There's a rule that you can, in a bank, you can only have you can connect about four parallel banks together, because thereafter the cable lengths start to be extremely longer. So that's something for you to factor in. Power factor, this is something that will not apply to the typical uh, off-grid system, but when it comes to grid-tied, and especially companies and industries where they have a lot of uh, loads that affect power factor, the capacitive and inductive loads, all that, there's something that you'll need to factor in as a designer, because you injecting active power from the solar panels from the solar plant is going to derate their power factor, by the reason that you're offsetting active power but maintaining the reactive power that initially was used to calculate the power factor bank that they would already have existing. By doing that, it means you're increasing the angle, the power angle between if you know the power triangle, you're increasing that angle. Increasing that angle means low power factor. So the next thing again to consider is utility grid power quality. These are voltage of the grid, mainly the hysteresis, all that, you know, so all the power quality issues that you would come by, you need to factor in a grid tied system. It will affect how I told you that the grid inverter needs to a reference voltage as well as frequency. It must match the grids. So if the grids voltage and frequency keeps on changing a lot, your inverter will keep on islanding. It will keep on going off to protect itself. So there's that in return, it's going to affect your plant. So guidelines for stringing solar modules. The first part is requirement for an inverter or a charge controller. From those, if you get a data sheet, things to watch out are the maximum DC input voltage of that inverter or charge controller, the start voltage, or rather the minimum voltage that you can connect to it, the maximum input current, and the number of MPPTs, because MPPTs equates to the the number of strings again you can connect to that particular inverter or charge controller. Yeah. So maximum DC input voltage. A string voltage should not, the string VOC, that is the number, the string VOC should never be more than the maximum DC input voltage of an inverter. If your inverter is rated at, for example, a rated inverter, someone tells you 1,000 volts, you cannot go, your string cannot come to 1,000 volts or above. It should be less than that. So the way you do that is you take your individual module. If you look just to your right, it will be like IC and VOC. You will take the VOC of the module, divide, and the VOC, the maximum DC input voltage of the inverter recharge controller, and then you divide it by the VOC of a module. That should the number that you get should be the maximum number of modules you have in series. Okay. The same thing again about maximum input current. You take that value given to you on the data sheet of the inverter or charge controller, you divide it by the ISC of the module. That should also be the maximum number of parallel connections you can have to that inverter or charge controller. That's it for that. So again, back to shading analysis. This is something that they have written can be done using softwares like PVSys or by mathematical calculation. So for PVSys, for those who have ever had the chance of using a PVSys software, there is something, if you look, there's always going to be a section about near shading. There's something like that, near shading and horizon, the horizon shading. So near shading, when you need to factor that in, you have to draw this, you have to have your module layout, all that in the PVSys for it to then, and then you also have to draw the shading object for it to calculate that and factor it in your calculations for the rest of the year. It's more accurate than in terms of estimation of the generation, it's more accurate than mathematical calculation. Mathematical calculation can just help you with offsetting your modules away from that shading, the effect of that shading object within a given time. For example, you can say, I need the shade to have left my modules at exactly 8 and at 5 in the evening. So there are two types depending on the direction, mathematical. We have east or west direction, depending on where the object is. So the formula for that is the height of that shading object times this times side bracket the sine of the azimuth angle and the tan of the altitude. Both azimuth and tan and the altitudes, if you go to, for example, a site called sunposition.info, I've indicated it there, you will find, and then you will go there, you input your location and the date. It will give you the azimuth and the altitude per hour, depending per hour or per every 30 minutes, depending on what you set. Mostly we consider June and December for, those are the days when the sun is at different locations. You'll get your maximum shade length during those, especially December, because it's a shorter day. You'll get your maximum shade length on those occasions. So for morning, you consider, if that is east in Kenya, you'll consider the morning altitude and azimuth. You want to concentrate on values around 7 and 8. Yeah, because past 8, the sun is already, a little up. On a good day, the sun is up and you want your generation to get start immediately. In the evening, at around 5, you want to concentrate at around 5. Yeah, or yeah, around 5 when the sun is going down. Or if it is a setup where maybe it's a company and they close at 4, you can then consider values at 4. Yeah, so depending on the shading length that you get, you have to then now give a clearance. The first module has to be cleared at least that length from the shading object. The north side, the north and south direction shading objects as well. What changes in the formula is that now instead of using a sign, use a cos. Yeah. So, but everything else remain. Where you get the information is still the same. Yeah, there's something that can just help you during your site analysis when you don't have time maybe to do the drawing on the software and all that. So I've been talking about drawings. These are some of the design drawings you need to be having when you are serious to communicate what your solar system really is all about and make any other person understand what's happening. You need to have single line diagrams. This needs to capture from the module all the way to where you're feeding your power. Yeah, it needs to be shown clearly with capturing all the main equipment, capturing the cable sizes and the cables, capturing all the fuses, switch gear protection, anything, name it, it needs to be captured in that single line diagram. Module layouts, this pretty much needs to show how your modules are installed. So you need to have a drawing of that. If it is on top of the roof, someone should be able to see how you're going to put your modules on a roof. If you're going to have them on a structure somewhere, it needs to communicate properly how you're going to have them there. The module mounting structure as well needs to be, module layouts modules can be put in either landscape or portrait with regard to the roof or wherever it is that you are ground mount or the mounting structure itself. They can't be put in terms of the landscape or portrait. Other factors will come in that you can consider if you need to make it a little bit more efficient in terms of stringing. You will come to realize maybe if I have them in portrait, I get to save on some meters of cable. If I have them in landscape, I get to clear away from this and that. I get to clean them easily. So those are things you really need to figure out when you're doing that layout. Module mounting structure, again, you need to show how you're going to secure your modules. What are you going to use to secure them? For when it is a roof structure, you want to make sure that your structure is not, you're not going to have your structure go into the roof and later on you have leaks, all that. You want to make sure it will hold the modules properly. If it is ground mount, you need to make sure it's strongly, rooted into the ground. So again, that's another choice for you to make as a designer. The system earthing and lightning and protection system layouts. Solar, it's a very solar is a very expensive, I would say, investment that you also need to protect. So earthing needs to be thoroughly done according to the standards out there. You need to aim to have there's something we call earthing resistance. It's always good to aim to have an earthing resistance of less than 5 ohms. That is for your earthing network. So things to earth in solar are you need to earth the module frames. The module frames are earthed, the module structure is earthed, and the inverters, every metallic part, and the AC side has to be earthed. If it is on a rooftop and you need to have lightning protection systems, again, there are different ways. There are instances when you'll have to join your lightning protection system to your earthing system, the general earthing system, but there are also instances when you should not do that. So again, I would encourage someone who would be interested in this to look for the IEC standards on that. Yeah, it's pretty much it's a wide document that tells you and shows you when you need to do what. Yeah. So then there is the equipotential bonding where necessary. Again, that's what I was just talking about. There are instances when you have to have all your every metallic thing in your plant has to be bonded to an earth, an equal earthing point. That is your AC earthing, your module earthing, and your lightning earthing. You need to bond them. You need to have a ring of earth, yeah, around that place. So, and then shading analysis layouts where appropriate. If you want to show, you need to show how far away or which part of your array will be affected by shadows and at what time. Again, that's something, a key information to share with people who are interested in that project for whatever reason. Lastly, solar PV maintenance practices. So once you've built it, you've designed it, you've built it, you have to maintain it. Yeah. Maintaining it means you have to wash the modules. And by washing this, just using brushes and water, you're not supposed to use any detergent on solar modules. It will affect the glass, and that again is going to affect the ability of the rays to reach the cells. So the water also, the type of water to use, there is a whole list of requirements for that. You need to do a test of that water to know the different salts in that water, the hardness, general water hardness. But generally, if you do any washing with the water, and then after that you see, the whitish settlement on top of your modules, never use that water again to clean those modules. In the long run, it's going to spoil your modules. You need to dust off your inverters. Inverters, most of them are put outside or just in areas where they tend to get a lot of dust, because also they have fans. So with time, dust settles around the fans and all. So you also need to try and clean that as much as possible. These are equipment that need to last you 10 to 20 years. So you need to take good care of them. Cable insulation tests. This is cable, the more you use it, there's cables, the insulation of it, cables break down. There's something that you want to be on top of every now and then, because the moment insulation breaks, a short circuit, you don't know what that could lead to. It could lead to a lot of losses of property, life, and all. So that's something you need to be looking into almost at every given time you visit a site or your plant. DC parameter measurements and IV curve tracing. Again, this is something you have to be on top of. Maybe your module might be safe today, it's working properly, but 3 months later on, you don't know what happened to it. So the only way you will determine if, for example, you might have an array of thousands of modules. The only way you can know if you have a problem with any string is if you do these measurements. Yeah, you have to do some inverters and will tell you some, but if it's just a small scale, again, but it's always still important for you to do this. And the IV curve tracing, this also is what shows you the change in the relationship between the voltage and the current, VMP, and IMP or VOC of that module. It needs to be within permittable uh, quantities. So check for any loose connections. Again, just like cable insulation test, loose connections can cause a lot of havoc, especially on the DC. We are talking about, for example, the grid tied systems. We're looking at systems of around even 1,000 volts. So in arcing with that high voltage could, even though the current is low, but it will still be, it could lead to a lot of losses. Also on the AC side, it's not safe. MMS, these are module mounting structure checks. You need to check them to make sure they're not rusting, they're in proper working conditions and all. Then checking physical conditions of modules. Just walk around. Are they clean? Are they properly secured? Or maybe a wind blew recently and they're loosening or something. You need to check that. You need to make sure that none of them is broken, if any. Then number 8, the daily remote monitoring of systems. Most of the good brands of solar equipment will offer you the ability to monitor the performance of your system on a daily basis, or even rather 5 minute 5 it's real time. Most of them are real time. You can see it wherever you are. You can always see what's happening. How, if your system is down, they will send you errors of what could have been the problem. You need to go check those. Then lastly, performance ratio calculations. Performance ratio, for those who have looked at PVsyst, again, this is something that there's a factor of how efficient is your solar system. In that, you need to, even when you're installing a solar system, you have an objective. It needs to be efficient. So this is something you need to do, carry out every now and then, as stipulated by your agreements with the parties involved. Even just for your own consumption, you need to try and do performance ratio calculations on your solar PV system. This will indicate to you how efficient your inverters, the general plant is in relation to the DC input vis-a-vis the AC output. Yeah, it's more like efficiency, but that factors in environmental conditions. Yeah, so irradiance and all. I think in terms of speech, that is what I had prepared for us. Now I'm going to give us the time to ask questions. Yeah, and also, yeah, just if someone has a burning desire to know something that I didn't capture within my small or my notes. Yeah, back to you, sir.
Okay, thank you, Steve. That was very informative. So, maybe anyone from the row with the question. Yeah, can unmute and ask or drop on the chat. Checking on that.
Hello, I have a question.
Yeah, sure.
What does power logging entail, and how do you know if your load estimation is correct?
I'll just answer each question after it's been asked, so that I get to leave any. So power logging entails, okay, there's the equipment out there that you use to know your consumption. So pretty much it's like an energy meter, but one that is going to record that data, your consumption per minute, per second, per hour, real-time consumption, store it somewhere or send it somewhere depending on how you set it up. Then based on that, you can be able to tell how your plant or your facility is consuming power. So you need to have those power logging equipment. It's just an equipment you attach to your, for example, if I have Kenya Power coming into my house, yeah, just immediately after after their meter, I can go there and attach my power logger. The device has, sorry, I can hear echo, but the device has a, the devices are meant to have CTs, the current transformers, and then we also have the ability to tap voltages. Then based on this, it will calculate your power, your load connected at every given time based on how much current is drawn, right? And also based on that, it will be able to then calculate the your energy usage at every given time. After which, maybe you've logged for 1 week or 2 weeks, you can go then get your data, retrieve it, analyze it. By analysis means you have to go there and look at the, for example, the peak power that was recorded, or the average power. So you have to do like data analysis on an Excel or something, come up with graphs, get your average power consumed by that facility or that client, whatever it is. After that, you can also see the total day, or rather daily kilowatt hours consumed, get averages of what makes sense out of it. Because sometimes you might find when there are days when they're not using a lot of power, but now you have to concentrate on the key days when a lot of power is consumed. That's it. So on to your second one, how can you know if it is efficient? That's why I mean, based from calculations, there's no way to guarantee that, especially even if you are to calculate it from bills, because bills themselves are not uniform. Maybe this time around someone consumed 20 units, the next time you see 30 units, then maybe 3 months ago they consumed 60 units. So you can't really tell what happened. You might decide to use the highest to design your system, but maybe so the person or you had decommissioned one of your loads that was making it to go that high. So the best way of always doing this is logging power, or if it is a large scale, it's an industry or company. Kenya Power has online platforms that also give you real-time data for the consumption of that. So you can ask for the loggings and get that. So whatever you do, always try as much as possible to log data. If it is a new plant, then in that case, you'll have to, for example, someone maybe just wants to have solar in their house and they're just about to move in. They've not, probably they have some equipment. You have to you have to go and record all those equipment. You have to figure out how many hours of usage this will, each equipment will be using, or the client will be using. So it's going to be an interactive session between you and the person who wants the plant, or you and if you know what you want to achieve. For example, the project that you are working on, about the one you're trying to design right now. If you already know your projected loads, right now you're doing a load estimation based on projections. All right. So your projections need to factor in a lot of safety nets. You need to ask yourself a lot of ifs, what ifs, and also to have limits. Because, for example, if you designed your system to be 2 kilowatt,
I guess I lost you. Don't know me or from all of us. Monica, can you confirm from your side if Steve is still
We
audible?
lost him.
Okay, Steve,
Lost him too.
we can't get you. Let me try. Steve, we can still hear your audio. Somehow you lost that. Maybe in the meantime, as we prepare the questions, I have seen people asking if the session is recorded. We have recorded the session and we'll be uploading to our YouTube channel. That's right, Moy. We have a playlist for the ones I have shared the link for all the trainings we have done as uh, in uh, in line with the project, the Smart Kibanda project. So you can follow the recordings there even for the previous one. We have done product development, project management, leadership in engineering project, financial engineering in project. Yeah, so you can follow that. We also be putting up this recording there.
Hello. Sorry, guys. My network just acted up. Sorry.
You're back now. Hello, Steve. You are now
Yeah.
back.
Yeah. Sorry. My network just had a small glitch there. But I'm not sure whether the last question was answered properly or if satisfactorily.
I lost you when you're talking about the factors, the if factors to be considered.
Oh, yeah, I just say, let me just explain that. I said that, for example, with your project, you need to know the exact, and the type of loads you're going to have. Yeah. For like with your setup, you need, if it is the project you're working on, it's a setup that I'm sure you already know the loads you need. So based on that, you also know the number of hours you're going to, or you expect to use them. Yeah. So that is what you need to make sure is accurate as possible. Since there's no log, you can't do any logging to be very sure about it. It's about load estimation. So your load estimation must be accurate. You must factor in all loads that you expect to have. Yeah. And then you need to also have a safety factor for that, so that just in future, in case anything happens, then also, depending on the loads, I don't know whether, if, for example, you have inductive loads, these are like, we're talking about something like, for example, you have motors. Yeah. If you have a motor and then, the starting currents and all that, for example, if it's a single phase motor, we are looking at about even up to 6, we're looking up to 5, 6 times the rated current. So it's very important for you to factor in such things. Which loads are you going to run, inductive, or they're just the normal resistive loads. So that is what I meant with a lot of ifs. You need to understand your loads, do proper load analysis and load estimation. Yeah. The point is, don't overload your inverters, don't undersize your system, but also don't oversize your system.
Nice. Great insights from you. So, any other question from the Okay. So if there is no any other question. Yeah.
I had a question. So,
Yeah, sure.
Steve,
Yeah, sure.
I could ask, but it's not based on the design. It's on
Yeah.
the aspect of marketing. Let's
Yes.
say maybe somebody is starting out now. because I believe maybe to be able to even get the experience in designing, you need maybe to have like real customers. So maybe what could be maybe the best strategy maybe somebody can use maybe to start out, so that you can maybe get moving and maybe be able to apply all these that need to be done to get the best system.
Yeah, sure. I'm first off, I'm not going to pretend to be in the know of the marketing bit of it, you know. So
Yeah.
yeah, but based on what I see happening out there, you know, solar is a service that has already been you know, it's proved that it's working. Yeah. So right now, what I understand, especially for, let me use the industrial and commercial setup, since that's where I am mostly. Yeah. For them, it makes more sense because again, the selling point is it's cheaper to have solar, yeah, than pay KPLC. So most of them save up to about even 40%, yeah, of their monthly, spending that they would have otherwise paid KPLC. For example, uh, a normal C1, CI1 client will pay around 12. That is just a tariff. Yeah, that's just a tariff. CI1 is a tariff for KPLC.
Yes.
So CI1 client will pay about 12 shillings. Yeah, per kilowatt hour consumed. That is minus VAT. Yeah, but then if for solar, once someone with solar comes and sells them this at around 8 shillings, you get there's already some good savings. Of course, it's little if you look at it from like, yeah, 12 to 8. That's like 4 shillings. But for people who are used to paying millions in a month, there's some good saving. Plus, you know, for grid tied, especially grid tied systems, the payback period is between 5 to around 6 years, depending on the sizes, yeah, and also how much you consume it. But mostly it will run between 4 or 5, depending also on the environment. You can remember the sun hours that we were talking about; those also will affect your return periods. So let's use just about 4 to 7 years. So this person will have gotten back his money that he invested, yeah, if at all he bought the product himself or she bought the product. They will get their money back, the investment, after let's say 7 years. But now they have 13, they have like 20, about 20, what would I say? No, about 17. Yeah, about 17 to 18 more years of using this power for free. Yeah. So that is one selling point for solar for C&I clients. Another selling point is that we have people right now in the market who their main thing in the solar field is just to finance projects. Yeah, they will come to you as a client and tell you, give us a space to build the plant. We are going to build it. Yeah, once we are going to build it, the only thing you'll be doing is buying the power from us, the generated energy from us, at, let's say, even the 8 shilling we're talking about, for X number of years. Yeah, you as the client, you have nothing to do on this plant. All the maintenance activity will be theirs. Everything will be theirs for depending on the contract period. Let's say even it's just 25 years, the full lifespan of the product. But remember, after 25 years, the solar modules will have depreciated by only 20%. Yeah, based on the company, that is now the company data. Solar panels only depreciate by around 20% in 25 years. So if I had like a 300-watt module, yep, after 25 years, I will still be able to get 80% power of that rating, assuming the right conditions are met. So it's something that is the concept is there. Those are some things you can mention. If someone is interested in solar and they have the right amount of loads, they consume a right amount of energy, that would make an investor come and give them the power plant without them investing any shilling. Yeah. So yeah, that's also another way of selling it. For residential systems, there's one out there. It becomes a little bit tricky, by reason being that, first of all, most residential systems are hybrid systems. Anywhere where batteries so far the prices have still not been very favorable, especially lithium. Yeah, and even if you do lead acid, we go back to the lifespan. So we're seeing after every 4 to 5 years, you need to be replacing them. For lithium, it could take you up to 15 years, but the upfront cost is very high for that. So for such clients, it's a little bit difficult to sell it, because you can't, in this case, you can't do the comparison between KPLC, the cost-wise between Kenya Power and solar. Because in that case, Kenya Power is going to win. Someone would tell you would rather pay, or would rather be buying pay KPLC, but not buy solar for that huge amount. So the thing here with that, the only problem we have is that, or rather the good selling point for a residential client is about the power, the guarantee that they're going to have power. It's unfortunate that our power is not very reliable. It's not the most stable. So it's just downtime. For solar, it's going to be more a good backup, cheaper than generator. It's a cheaper option than the generator, by running generators sometimes. So those are some of the key points you can look to discuss with your potential clients. Yeah.
Okay, thank you.
Yeah, sure.
So that Marceline, you want that question?
Hello, thank you. If you can hear me. So
Yes,
I'm
yes, I can
Marceline,
hear.
a student from KU. So thank you for the comprehensive talk. It was really great and enlightening. So I have a few questions. First of all,
Yes.
I realized that in the AC multimode system doesn't have a charge controller. Why is it so? And then I didn't quite get what is exactly the function of a charge controller? Is it to prevent overcharging and undercharging of the battery, or what else does it do? And then you also mentioned about the maintenance of the PV system. Could you also highlight some of the maintenance of the batteries that are being used, if they're kind of related? Thank you.
Okay, sure. I'll start with the first point was about you didn't notice on the AC, you didn't notice the charge controller, right? If I'm correct
Yeah.
on that. So yeah, that is the AC coupled system, right?
Yeah.
Yeah. So for AC coupled system, you can remember I told you we have, in this case, we're going to have a bidirectional battery inverter. Yeah, such battery inverters are also called they're like charging inverters. They have inbuilt charge controllers. Okay, so they can charge. When they're converting from AC to DC to charge the battery. So internally they have their charge controllers to control that process. So you don't need an external one. Okay. And also by the fact that your PV array will have been connected your PV array is connected onto the grid inverter. So the grid inverter does the conversion of the main DC into AC, and then your battery inverter with its inbuilt charge controller will do the charging of the inverters. And yes, you're right. The charge controllers, as the name suggests, it's just to control the charging of a battery by varying the voltages, currents, when to charge the battery in a bulk way, when to equalize them, so that all the batteries can be of the same voltage when they're fully charged and all. So that is pretty much what the charge controller does. It's just to make sure that you don't feed. For example, the example I gave with the MPPT of feeding, you have a panel that is 40 volts, and you want to charge a 12-volt battery. So now it's now the ability of that charge controller to bring down that voltage, the module voltage, to the same voltage that the battery needs to get charged, while playing around with the current. So that is the main objective of a charge controller. And to your last question, yes, in terms of maintenance, batteries, the main thing, again, first of all, it depends on which battery. Okay. If it is, for example, a flooded lead acid battery, you'll have to be topping up, the battery using the depending on which chemical it uses. You'll have to be topping it up, changing it now and then. So it depends on which batteries, but most of the time for batteries as well, is just to make sure what I told us about these connection points, the terminals of the batteries, just make sure it's fine. For batteries, you need to make sure that they are all charging and discharging pretty much almost with equal internal resistances. So by that I mean, if you're going to buy batteries, you must make sure that all your batteries that you have together are of the same age. I can't connect a 2-year-old battery with one that I've just bought today. For the reason that they have totally two different internal resistance. The one that was bought 2 years ago and has been used will need a lot of time to charge, while the one that I've bought today will charge properly within a given time frame. So while the second one, the older one, is trying to get fully charged, the new one is getting overcharged. So that's why you never mix old and new batteries. That is like a rule of thumb, especially lead acid batteries, and also even some lithium, except for some that when the manufacturer tells you you can do that, which are also very rare, but that is it. For your batteries, never mix old and new. Also try to maintain that depth of discharge. You don't want to be draining your batteries every now and then. Your storage of the battery, you need to follow all the instructions as per the manufacturer. All in all, when it comes to maintenance, operation and maintenance of all the solar equipment, as I usually say, the first thing you always have to make sure you've done is read the manual. Most of us don't like reading manuals, but the only person who knows more about that product than you is the manufacturer. So please, always take time, go through the manuals. You will find, because even installation, there are things that they're going to recommend that you do. They might recommend cable sizes for you. They might recommend protective switchgear for you. All those. So you need to try and do what they've told you, because then also you will get to maintain your warranties. Because you can't do whatever you want, that it's right. It might be technically right, but it's not something that is warranted. So always go back to the manuals, read properly, go look. They have maintenance of their products. You need to do that. But for batteries, keep them clean, keep them well stored, in proper conditions. If it is about, some of them require, there's operation temperatures of batteries. Most I've not seen them go above 60 degrees. So you need to, and also go so low. So you need to maintain that. If you have to buy an AC unit, to make sure that all these things are within the right temperatures and all, you have to do that. Thank you.
Thank you so much, Steve, for the informative session. I am Ben. So I have a
Yeah.
question.
Yes.
What would you consider as a smartness for solar for the
Yeah.
people in the informal sector, especially for the aspect of security?
Sorry, just repeat that.
Asking what would you consider as
Yeah.
smartness for the people in the informal sector in the aspect of security?
In the aspect of security, smartness of what exactly? I'm not getting your question properly. Maybe if you could
I'm
word it
saying,
differently. Yeah.
I'm saying, what would you consider as smartness in
Yeah.
solar, whether whichever installation or in whichever way, for
Yeah.
the people who are living in the rural areas in
Yeah.
terms of security, like where the solar cannot be stolen, how should it be placed, in terms of smartness? What would you consider smartness in such a scenario?
Oh, okay. I mean, I don't think by the fact that someone is in a village or something else, it's supposed to affect the general, way of how to do your electrical designs and all, because this equipment they need to be installed in a given way, and they must be installed in that way. So in terms of the security of the device, that's something else totally different. But in terms of security of the personnel using it, you have to then, you as the person who has designed it, that's why you have to really inform these people, educate them on how to use them. The other thing about it is, and you let me know if I'm really tackling your question the way you'd want it to be, but also something else to factor in terms of you need to do a professional job. One issue I've had with such type of systems is the level of unprofessionalism that goes into it. Yeah, because for example, when I was talking about batteries, you will find someone has used the car battery instead of a solar battery. That's again, from a design perspective and the general operation of a plant, it's an issue. So not just avoid shortcuts. That I would say that's a smart way of going around things, and then educate the people in the village or wherever they are how to handle these things in a good way, in a way that they don't interfere with them. I don't know whether I did get it right. If I didn't, feel free to just press on and ask me more on exactly what you needed to hear.
Yes, thank you. Thank you so much. Asking this because in our Smart
Yeah.
Kiosk project, we
Yeah.
are tasked with making the solar be
Yeah.
also smart in terms of
Yeah.
making a better environment for the mama mboga there. So
Yeah.
as part of the things that you are considering was to get to look at how can we make solar security in terms of
Yeah.
smartness. But thank you so much. It's clarifying. Okay.
Okay. It's okay. I mean, it's based on your product. I think we can always reach to me, and we can always talk about and understand really what you guys had in mind. But in terms of if it's just smartness about security of the equipment, that again, it's not like you can prevent someone from. The only way you can prevent someone from going to tamper with it is if you have it being watched in a way. Yeah, you can't just put it there and leave it. But also for the mama mboga, because it's this mama mboga needs to really understand how to use this equipment without interfering with it. You will have to give them the guidelines of how to operate that equipment in a professional way so that they avoid anything that would lead to chaos later on.
Sure, sure.
Hello, Steve.
Yeah, hello.
Maybe from curiosity, I was wondering what would happen to a system, off-grid
Yeah,
system, when
yeah.
you designed it without a charge controller, like you connect the panels direct to the battery.
Uh, that, you know, Okay, what would happen is, first of all, there's a very high likelihood your batteries will be damaged. Yeah, because there's nothing really standing in between the module and the battery. But also, again, the charge controller usually gives kind of like I would say a stable output, regardless of the instability on the input side of it from the modules. It gives a stable output to the batteries. Okay, so in the event you remove that, because solar panels are affected by environmental conditions. 1 minute its voltage and current is going to be the X value. The next moment a cloud has covered the sun and it has to change, so that your batteries will be damaged. And you don't, let's just say you don't want to try that, because there's also a high likelihood batteries have a habit of, if you do it wrongly, other than getting damaged, sometimes they can blow. So you need to try and avoid that. Just no shortcut in that.
Okay, sir. Thank you. So I see Monica's hand is up. Maybe Monica, you have a question, the last one. Because
Yes,
maybe
I have a question. So when you're talking about designing and under the inverter, you said we should always go higher. Does it apply for all the components? Let's say after coming up with the size of the battery, I've realized my value is just slightly higher than, let's say, one battery, maybe
Yeah.
by a few decimal places. Should I still go higher, or is it possible for me to ignore the difference and go for a lower sizing?
Now that, let me say, if for me, I would advise you to go higher. If at all you are still aiming to achieve the same results that you needed, it's better to have extra than to have a short. Yeah, to be short of something. But if you having one, for example, your battery, if it's still going to serve you well, yeah, then yes, you can stick to that. But if for some reason you're very sure that you're going to have issues, just always go for the higher, because in the long run, you're not going to be able to achieve your target. Okay. If, for example, you consume that is with my example earlier of you consume 1 unit, you want to store 1.2 units in a battery. That's like literally having one battery of 12 volt, 2200 Ah. That's 2.4. Then you set it to a 50% DOD. In that case, you see it will still work, right? Even if, but if again you increase them, the only thing that will be affected, especially with batteries, is if you maintain it. Yeah, if you maintain it, that two things. If you maintain it, your DOD will have to you can reduce your DOD, yeah, further to incorporate the extra that you need. You can play around with that. But if at all it's not, you can do without it, then you can maintain. The other thing is, for example, if I was doing my calculations with a 48 volt system, or rather 24 volt system, I cannot now all of a sudden, for example, if a 24 volt system, I need at least two batteries of 12 volt. Yeah. I can now not settle on one if my system is going to be 24 volts, because one battery means I'm not going to achieve my 24 volts. The same thing with 48 volts. If it is 48 volt and you're using the normal lead acid batteries 12 volts, you need at least four, or rather multiples of four. You must always be able to achieve that. Removing one is always going to affect you. You cannot string them properly. So it's something that, one, it's a decision you have to make as the designer relative to the energy demands. If there is no harm to the client or you when you reduce it, then fine. But if there is harm, then it's better to just increase it. If, for example, I remove one panel, okay, that means I'll not be able to achieve my energy target within the 4 hours that initially I'd used to design. But if I add one, it just means that I'll get it within probably a shorter time with a fraction of a few minutes. Yeah. So there's that. The problem, don't over increase it, then now the cost becomes excessive, but also don't undersize it such that it does not really help you.
Yeah, I guess that was answered.
Yes, it has been answered. Thank you.
Yeah, okay. I thank you, Steve, very much,
Yeah.
very much, for sparing your time. It's almost 2 hours of training. I guess now as we proceed with our project, we keep you close as we design our system. We will like you're breaking, Steve.
Sorry, no, I see a hand raised.
Ngetich, okay, so Ngetich, I'll give you this chance as the last person.
Okay, I have a question.
Yeah.
In this design, the solar the controller,
Yes.
is it in a position to like during peak hours when there is enough solar and the
Yeah.
state of the charge in the batteries, when
Yeah.
it is fully charged, is it in a position to isolate the batteries and then consume power directly from the solar?
Yes.
How is it?
Yes, it is. But what do you mean? Okay, it is, if it is a charge, you're talking about the charge controller, not the battery inverter, right?
Yeah. No, I remember you said it is
Yes.
integrated with the inverter.
No,
If
yeah,
I'm not
there's
wrong.
one that is external, but there's one that is internal, depending on which battery inverter you have. But regardless, the point is when your battery is full, the energy generated still has to be, it will be fed directly to your loads. Okay? Yeah, so whether it's DC coupled or AC coupled, whichever time once your battery is full, the attention will always be given to the loads. So yes, nothing is wasted.
Okay, so the batteries also are protected against overcharging.
Yes, once it's batteries communicate with the charge controllers, right? And even the inverters. So that communication, and also the charge controller will monitor the battery voltage and current status as it's charging. Yeah, they are smart enough to know when the battery is fully charged. Once it is fully charged, yes, that it will just bypass the battery and
then go direct to load.
Go directly to it will be converted directly to the AC. But okay, this is in an instance when, for example, in an off-grid setup, if you have an external charge controller, right?
Yes.
And a unidirectional battery inverter that is just giving from AC to DC. There are those inverters that don't run. For example, maybe at home in the villages, I see some people have some inverters that it's switched off and the charge controller is always on. So in such cases, when the charge controller is done charging the battery, of course, it cannot take the excess power anywhere, right? But if your inverters are always on, everything is always on, yes, it will be fed directly to your loads.
Yes, I think.
Yeah.
So Steve, once again, I would like to thank you. That was a very informative, intense session. I guess everything was well covered, and also I saw the audience still remained to almost the last hour. So I was saying maybe as we proceed with the project, our hope is to get it right the first time we do it. So we hope to to keep you close so that can help us.
No, it's fine. It's fine.
Yeah, okay. Also, I also wanted to request from you if we can share these recording on our YouTube channel. That is for Imoy for future reference and anyone would like to reference from this.
Oh yeah, it's
So
fine.
that is okay, sir. Thank you. Yeah, so
Okay.
I thank everyone who was staying to the last minute. Thank you very much from us to you. I would like to wish you guys a good afternoon. I'll share the recording through our YouTube and through your mails who registered and through our group, our chat. Yeah, thank you very much, everyone. I would like to wish you guys a good night. Asante sana. You can leave again.
Thank you very much as well. Bye.